Okay, thank you. Hi everyone, I'm Giordano D'Aloisio, and today we'll talk about enhancing fairness in a classification task with multiple variables through a data and model-agnostic approach. This work has been made with Dr. Andrea, Professor Antinisca and Professor Giovanni Stilo. We are all from the University of L'Aquila. Okay, so here is the outline. So we'll start with an introduction and a description of the problem. Then I will tell the fairness definition we are using in our work. Then I will describe in more detail the proposed approach, which is the Debiaser for multiple variables. I will tell the experimental evaluation, and finally I will make the conclusion and describe some future works. So, as all you may know, bias in machine learning has acquired a lot of relevance in the last few years. We have spoke about bias all the day. And in particular, we talk about bias in a more general way in machine learning when there are individuals or groups which are discriminated on the basis of a set of so-called sensitive attributes like gender, race, and so on. If this bias is not managed, it can lead to severe discrimination and unfairness. And here, just as an example, I show you a picture from a website about one of the most famous biased systems, which is Compass, which was making discrimination among black and white people in predicting crimes. Now, over the years, many methods have been proposed in order to improve fairness. And from this picture, we can see that most of them are for classification domain and for individual, for fairness, group fairness definition. However, we have seen that the multi-class classification problem, which is very common in a lot of domains, is still not fully being addressed. And so for this reason, in this paper, we present the Debiaser for multiple variables, DEMV, which is a model and data agnostic pre-processing algorithm to improve fairness both in binary and multi-class classification with any number of sensitive variables. So this is a pre-processing algorithm, meaning that it is applied to the dataset before sending it as an input to the classifier. Now, before describing in detail the proposed approach, let's first see the fairness, the definitions that we have used in our work, which is the very famous statistical or demographic parity, which states the independence among the predicted positive label and the sensitive variables. So in particular, the probability of having the positive label predicted should be the same for the privileged and the unprivileged groups. A different formulation of statistical parity is the disparate impact, which instead considers the ratio among these two probabilities. And in this case, this matrix should be equal to 1 in order to have optimal fairness. Now, here we can see a high-level overview of the main steps of our algorithm. So the main idea is that we have to identify all the so-called sensitive groups, which are made by all the possible combinations of the values of the sensitive variables and the values of the label. Then we have to perfectly balance these groups individually. Finally, we merge them together in order to have a fully balanced and hopefully fair dataset. Now, let's see each of these steps more in particular, in detail. So the first step of our algorithm, again, is the identification of the sensitive groups. And here we can see a picture of how this process is done. So we basically build a set of Boolean conditions, each for any combination of the values of the sensitive variable and the values of the label. In this example, we are considering an hypothetical dataset with 2 binary sensitive variables and a binary label. But this process can also be applied to categorical sensitive variables and to multi-class labels. Here, for sake of simplicity, we are only showing categorical binary values. Then we identify the sensitive groups by filtering from the original dataset only the items satisfying the given Boolean condition. And in this case, for example, we have 8 sensitive groups. Then for each of them, we compute its observed and expected sizes. These two values are given by these two formulas here. So in particular, the expected size is the product of the portion of items satisfying only the condition on the sensitive variables and the portion of items satisfying only the condition on the label, while the observed size is the portion of items satisfying both the condition on the sensitive variables and the condition on the label. Then we enter the so-called sampling loop. So basically, we compute the ratio among the expected and the observed sizes. And if this value is higher than 1, then it means that the observed size is lower than expected. And so we have to randomly duplicate an item from the group. Instead, if this value is lower than 1, then it means that the observed size is higher than expected. And so we have to randomly delete an item from the group. Then we recompute the observed size and repeat this process until the expected size and the observed size are equal. So the ratio becomes equal to 1. We do this process for all the sensitive groups, and then we merge them together in order to have the fully balanced dataset. And here we can see a picture of this sampling loop. So in this example, we have 4 sensitive groups, and we can see how this ratio finally converges to 1 for all the sensitive groups. Now let's describe the experimental evaluation that we have conducted. So we compared our method with the exponential gradient algorithm, which is a very established algorithm for multi-class classification. And this algorithm basically uses a min-max approach to find the best trade-off among fairness and accuracy when we have one actor maximizing fairness and another actor minimizing a given metric, given fairness constraint. In these experiments, we have used the statistical parity for binary classification and the 0-1 loss for multi-class classification, as suggested also by the authors of the paper. Then we used the logistic classifier and we performed a 10-fold cross-validation, computing the following metrics only on the testing set. So we have statistical parity, disparate impact, 0-1 loss, and accuracy. Now, considering our method, since DEMV has a, let's say, a stochastic behavior in the selection of items to duplicate or to delete, for each train test set, we apply DEMV and perform the given matrix 30 times. So here we can see a picture of our evaluation. So we apply DEMV only on the testing set. We compute the matrix only on the predicted label, and then we done this process 30 times in order to have an overall view of the behavior of our method. Here we can see the employed datasets, and as we can see, they are a very heterogeneous set of data, both in terms of scope and in terms of size. In particular, here we have the binary datasets, which are adult, compass, and German. While here we have the multi-class datasets. We have the CMC, crime, law, Trump, and wine. They are all taken from the bias and fairness literature. Okay, here we can see the mean and the standard deviation of all the metrics we computed on all the multi-class datasets. And in particular, in blue, we have the metrics for the original biased classifier. In orange, we have the metrics for the exponential gradient, while in green, we have the metrics for our method. Again, on the left, we have a matrix whose optimal value is equal to 0, while on the right, we have a matrix whose optimal value is equal to 1. And here we can see very easily how our method overcomes the selected baseline, keeping also a high level of accuracy with respect to the biased original classifier. Here instead, we have the same metrics for the binary classification datasets. And here we can see that our method is still able to improve fairness with respect to the original classifier. However, the exponential gradients perform better in such a situation. But we have observed that the standard deviation of our matrix is lower with respect to the exponential gradient. So it means that our method is more coherent in its performances, and so it's giving always similar outputs. So from the performance experiments, we have drawn the following conclusions. So we have seen that our method is able to improve fairness in multi-class classification domain, and it is also a better choice than the exponential gradient algorithm. Concerning binary classification, we have seen that our method is also able to improve fairness, but has more difficulty, especially when the starting bias is very high. We have seen in our experiments that when the starting bias is very high, our method has more difficulty improving fairness. And finally, we have seen that not always the best fairness is achieved with a complete balancing of the groups. And here we can see an example. So here we have the mean and the standard deviation of all the metrics at different level of iteration of our method. So in particular, on the left, we have the matrix at iteration 0, so for the biased classifier. On the right, we have the matrix for the fully balanced dataset. While in the middle, we have the matrix with a dataset with a partially balanced dataset. And here we can see, especially under the disparate impact, how the optimal fairness is achieved in the middle of the balancing process and not at the end. So in this work, we have presented the Debiaser for multiple variables, which is a novel approach primarily defined for the multi-class classification domain, but that can be also applied to binary classification problems. In particular, concerning a multi-class classification, our method is a better strategy than the selected baseline. Further, we have seen that performing a complete balancing of the groups is not always the optimal solution, like in the CMC dataset. We have also seen that our method is able to improve fairness in the binary classification. However, as expected, more, say, specifically designed methods like the exponential gradient can perform better in such situations. And in the future, we like to first investigate more which are the characteristics of the dataset that lead to optimal fairness before a complete balancing of the groups, so like the CMC dataset. And also, in addition, we want to evaluate our method more with a different number of sensitive variables, more metrics, more data set, and also and more baselines also, if they are not too much. So thank you for your attention. Here is the source code. You can, so if you want to test our method, you can scan the QR code, or you can follow the link. There is the source code of our algorithm.